Hello, everyone. Welcome back to Particle Physics for Teachers. I'm really excited today to be introducing you to my friend Steve, who's going to be doing the virtual visit of Atlas. So as I mentioned, Steve's a wonderful person, to me, a personal hero of particle physics, and he's introduced me to tons of people. I can honestly say this course wouldn't be happening if it wasn't for his help and encouragement. So it's wonderful to be here and to turn things over to Steve. Just before I do, just a reminder, like usual, please say hi and introduce yourself in the chat and mention where you're from. Steve was asking me just before connecting, where's everyone joining from? So he's curious. Also, for anyone who wants a certificate for attending all of the courses, then I need to be able to keep track somehow that you were here. So please don't be shy about saying hi. If you have any questions, and hopefully you'll have lots of questions, Steve's a very friendly guy, extremely knowledgeable. He loves questions, so don't be shy, especially if you feel like jumping on your mic and asking anything. If you prefer to use the chat, then I'll go through that. I'll relay questions probably as they come up, because Steve, like me, kind of likes being interrupted, and it's good to have an excuse to go on a tangent about things. So please don't be shy at all. Like I've said a number of times, Steve's a very friendly and welcoming guy, and I'm excited to be turning things over to him. So Steve, thank you again for joining us.
Thank you very much, Michael. It's really a pleasure to join this. In particular, the particle physics for teachers. This is something that we at CERN and on the different experiments over here have been hoping for some time. We all know that particle physics is actually a pretty simple topic if you stick to the simple part, and it's something that that teachers should not be afraid of. They should enjoy it. It's much more fun to talk about the conservation of momentum when you're talking about the search for dark matter than playing with pool balls. Although that's fun too. Playing pool is fun. But regardless, welcome, welcome to the Atlas experiment. My devices here for the Zoom are my arms and my phone, and I'll do the best I can. But I'm gonna the advantage of that is I'm gonna take you all sorts of places where I can't normally take people who actually physically come here to see the experiment. You can get a glimpse over my shoulder of Atlas. I'm going to be taking you inside, showing you lots of different parts of that up close and personal. I just want to let you know my background. I'm a particle physicist. I've been doing experimental particle physics here at CERN for 35 years now. I came here as a young child, as a graduate student, I can say. And it's just an absolute pleasure. I get to meet people from all over the world here. That's what CERN was exactly designed for. It was founded in 1954 to do science for peace. It was bringing together people from pretty much all the countries I just saw listed here in the chat when you guys joined. Countries from all over Europe in 1954, scientists who had been having to work on weapons and things like this back in the 40s for a world war, a terrible world war, who wanted to work on research and research for peace, and bringing them all together to work together here in Geneva was just an outstanding recipe. So I've been here not since 1954, but since 1988 as a student. And it's fantastic seeing all these people. Now CERN is populated with people from countries, from well over 100 different countries are here. People with backgrounds from various cultures and social backgrounds, linguistic backgrounds, etc. And that makes our science much, much stronger because you have people with different points of view, different ideas, and that's necessary when you're trying to make objective measurements. You need to have all these various subjective points of view to finally figure out that what you found is something that everyone agrees on. That's the challenge. So I'm here underground. I'm almost 100 meters underground at the Atlas experiment. We're one of the 4 places on the Large Hadron Collider where the photons pass through each other, where we cross the beams. as in Ghostbusters. We actually cross the beams at these places, and I'll show you approximately where that happens. At the 4 places, we surround the collision points with detectors, try to measure everything that comes out from the collisions. Now, the collisions happen very often. I'm going to turn this around and sort of show you the area where they happen. Okay, so we're going to point this up here. This is our little baby down here, the Atlas experiment. We're actually the largest of the experiments in the Large Hadron Collider. The protons actually come in from way over that way, and they go in through the detector, and they meet other protons coming from the other direction in the center. You can't really see that here. In fact, we can never get on the inside there because it's all closed up. We have brought out parts of our detector. We pulled it out so that we could do some work. On occasion, you might see some people inside there doing some work. We have some new components of the detector that need some fine tuning. That's what we call fixing, fine tuning. And so we have it in a configuration to work on it. There's no protons colliding. Now this is our year-end technical stop. It's a little bit longer this year because we wanted to conserve energy. When we made the plans, we didn't know what was going to be happening with the war in Ukraine and with the cost of energy here in Europe. So we cut our program short to make sure that everybody had heat in their homes. This does, to run the LHC and all of the experiments, does use quite a bit, several hundred megawatts of power. So it is important that we conserve right now. So here's the view. I'm way down on the floor. You can see down here. And the experiment from here all the way up is roughly 26 meters, so about a quarter of a football pitch. And from this end all the way to the other end, and I'm going to walk you down there, is about 46 meters. We build this huge thing simply because we want to understand the smallest components of our universe. And I know that sounds a little crazy. Why does it have to get bigger in order for you to find small things? But you guys all know Zog's rule. Zog was the very first of the cave people who smashed rocks together and discovered that the higher energy the collisions he made, the harder he smashed those rocks together, the smaller the parts that came off of it, and the deeper he could probe inside of matter. In modern day physics, that's simply that rule E equals h nu. It tells us the amount of energy is proportional to the frequency, meaning it's inversely proportional to the wavelength. So the higher the energy, the smaller the wavelength, and the more you can probe into matter. Zog knew this way back in the day, and then it took Planck and others to figure that out these days. But it's true. And so you need high energy. And if you have high energy, you have particles coming out from the collisions that are going very, very fast and which are hard to bend, even with very strong magnetic fields, to measure their momentum. And so you want a large distance to measure them over so you can see that curvature. The more they curve, the lower their momentum. And we use that relationship to figure out what's the energy of each of the tracks coming out from the collisions. And all of these parts here, these are detectors, active detectors, which tell us when they've been hit by one of those charged particles out here. So just to give you some more idea, I'm gonna walk up from here. If you hear any heavy breathing as I walk up, it's just an effect of Zoom. It has nothing to do with my age. I just want to make sure that's clear. I don't ride bicycles all over Europe and Africa like Michael does, so not in perfect shape. I'll make a first stop here, which I think is a very interesting place. This is the far end detector. This is our Muon system. As you guys all know, muons are just electrons that are more massive. But because they're more massive, they can make it all the way through the detector, all the way back to here. One of the principles we use to measure them, I already mentioned somewhat, is that you have a magnetic field that surrounds the detector. And that magnetic field, in fact, this components, this big sort of gear-looking thing that you see in there, that's part of the toroidal system, and the tubes that you can see at different places up here inside there with the straps on it. Those tubes are part of the toroidal magnet system. You surround the detector with a magnetic field so that charged particles as they leave are curved. So you have to know that the two principles you have to teach your students so that they can build one of these at home is that one of them is that you can curve charged particles with the magnetic field. And they use that to build the LHC. They use the fact that you can give them a little kick with an electric field to make them go to higher energies. And that's how the LHC works in simplistic terms. And then we use that fact to make the charged particles that come out from the collisions curve then so we can measure their momentum. So that's an important thing to know. The other thing that's important so you can build one of these detectors is ionization. So in the very center of the detector, a place I can't get you into, trust me, there's a lot of silicon in there. Silicon's great because when silicon is hit by a charged particle, it will knock an electron off. And that electron tells you that something came through here. And then it recovers very quickly, which is important for us because the collisions are happening every 25 nanoseconds. So in the very center, we get most of our data. It's silicon getting ionized. Out here, in this detector, we have these tubes and there's a gas inside there, argon CO2. And when a charged particle goes through that gas, it knocks electrons off and they're attracted to a wire, which is in the middle of that at a high voltage. And so the particle will go through, it will ionize the gas, those electrons from the gas will go to the wire, and then they'll go out and they'll get read out by electronics at the very end. The electronics in these different places in these boxes. And then it gets sent out to a big room of electronics next door. And here you can see also you have these patch panels here collecting the data, grounding copper, and tubes for the gas. Lots of copper tubing for the gas. And there's also some interesting things. We have cameras back here, and those cameras are used to align the detector. You can align it with these devices to millimeters, but then you want to know how much your detector has moved in microns, micrometers, in the data. You can correct for any slight movements. And that happens all the time because of heat fluctuations and just vibration. So you want to keep track of exactly where your detector is all the time. So you have some cameras to do imaging and let you know how much it's moved when it moves. So that's what goes on here. This is the Muon system. It's really the biggest part of the detector because all the way back here, this is the third layer. You have 3 layers so that you can measure the curvature of the track. And this is the furthest one out here. So I'm going to take you up. I'm going to go up. And maybe, instead of me just doing a monologue the whole time, as I'm walking up, if somebody has any questions they'd like to ask me, I can do my best shot at answering.
And that's a great opportunity to interrupt you as well. I was just about to say for teachers who are interested and looking forward to learning more about drift tubes and muon detection, remember in 2 weeks there's Jesus Puerta Pelayo who works at the CMS detector. He'll be joining us from Madrid, where he's head of outreach at CIEMAT, which is a national lab. And he'll be going into a lot of detail on how gas detectors like those muon tubes work, including what's it including? Like the history of gas detectors. There's also a teacher, a friend of mine from Italy, Federico Andrioletti, later on that week, who will show you how you can make a homemade rudimentary gas detector, but one that uses air rather than carbon dioxide and argon to show that principle to students in class. So these are things like they're all related. So heads up on what to expect. But that's enough for me. Does anyone have anything they want to ask Steve? And I see there's some questions in the chat. Either feel free to jump on your mic and ask, or if you're shy or don't have a mic or whatnot, I'll relay them. But let's give that a second for anyone who wants to ask a question themselves. Either what you put in the chat or another question. Let's see who's curious about anything.
Don't be shy.
Oh, and to relay Rodney's question, I'll put a link for websites where you can do virtual visits. So, well, should I answer this or should you, Steve? Because Atlas, you sign up different. Like for LHC experiments, it's different than other CERN facilities. I'll put links for all of those.
Sure, sure, yeah. I know about the Atlas virtual visits. I've helped the others to get going with virtual visits. I think they're all doing them now. So I don't know their system. Go ahead.
And I think you're the one who first started virtual visits for any CERN facilities, right?
Yeah, I claim that. I think it was me. It really started back when we first turned on the LHC. They'd given us special equipment in our control rooms, and that allowed our spokespersons, at that time, the Atlas spokesperson was Fabiola Gianotti, who's now our Director General. It made it possible for them to talk to the public and express their excitement about the startup of the LHC. It was only shortly afterwards that they decided they wanted to come by and take away the equipment, and I refused to let them have it. I said, this is too valuable. We're going to add a video conferencing system, and we're going to connect the classrooms. And so we've been doing that ever since.
And just as I'm looking up links for visits, so I'll first of all share everyone the link for the Atlas visit. So if anyone wants to sign up, and they can even, like for their own students, they could sign up and have you or one of the other people who guide around Atlas to do that for a school group as well. That's right, Steve?
Yeah, that's what we really love to do. I've gotten an opportunity, without riding a bicycle, I've been able to talk to classrooms all over the globe. It's fantastic. I love doing that. And it really helps. It helps the students to get going, to start thinking and to ask questions, because I really like to encourage that. And once they start asking, it just flows. And that's what's going to happen this evening as well.
And it's amazing too, like from a teacher, from a user's perspective, how welcoming and simple and easy it is to get someone like Steve to show you and your students around places like that. Like, I think this is the 4th time Steve's done a visit for me, and it was actually just from the general form requesting one. Steve signed up to be the guide, and he said, "Oh, that sounds interesting, the particle physics for kids course you're doing. Tell me more about it. Would you like to present it at Atlas Outreach, at the International Particle Physics Outreach Group?" So there's good people, not only Steve, he's not a one-man show. There's tons of other people doing this as well. But really do sign up for that. Once I find the chat again, because I seem to have lost it, well, switching windows to look up the link, I'll add the link, and I do highly recommend that. So that's an excellent question. There were some other questions. Does anyone feel like asking it themselves, or if not, I'll relay it.
How many revolutions? I haven't read that much. How many revolutions? How many do we need before we get the world back in peace? Is that the question?
Oh, it was how many times the protons go around before colliding?
Oh, that's a really good question. I'm not sure I can even answer that off the back of my head. They go in a second. They go around roughly 11,000 times. So they're going the speed of light, so to speak. Now, they pass through each other all the time. That's the tricky bit about this. They will go around and go through each other over and over and over again, and more than half of them won't get to collide. Kind of sad. They'll have traveled around for hours and hours. Typically, we fill up the machine with the protons, accelerate them, and then we start collisions. Once that gets going, it can last 6 hours or so. So you can, well, there you go. If you know it's 11,000 times a second, and that they are in there in 6 hours, and that roughly half of them collide, I'll let you do the mathematics. You can tell roughly on average how many times they go around before they collide. The trick about this is, so the collisions happen, inside there. protons go through, where we can see how the wheel curves like this, right around here is where the protons go through. They come in packets. Each packet or bunch, we call them bunch, is 100 billion protons. That's a galaxy. It's one Milky Way or one Andromeda worth of protons. Now, it takes a lot of work to squeeze these protons together into a very high intensity narrow beam to get them to collide. It's not easy. It's a tremendous amount of work that gets done by the experts in the LHC, the accelerator experts. And when they do that, we get roughly these days 60 on average will actually go through each other. So out of 100 billion against 100 billion, you get roughly 60 collisions. And that's really good. It took a lot of work to get to that. Now, the thing about that is protons, as you know, are not elementary particles. They're made up of elementary particles. They're made up of quarks and gluons. And so much of the time, the quarks and gluons will never really meet. And so you'll just get sort of electromagnetic scattering. And we've seen that before. So when that happens, we just let those events go. We throw them out. And that means that we only keep maybe 1 in 10,000 or so of the collisions. We'll actually keep. Why we keep it is what some of these detectors do. Actually, these ground detectors behind me are part of our trigger system. They detect when something's happened that's interesting. This system behind me here detects when a muon has gone through. On the inside, we have others which will detect if there's been an electron or a photon or just some energy deposit, something that signals that there was some interaction that happened between the quarks and the gluons. Then the trigger gets pushed and we take a picture of that bunch crossing and we keep it. That bunch crossing we write to tape and we keep that data. But as I say, most of them we throw away. We're getting a huge amount of collisions per second. So I hope you've done the math now. You figure out, let's see, 11,000 times 3,600 times 6 divided by 2 should have gotten you the number of times the proton goes around before it collides, roughly, on average. Maybe there's another question?
There's one about the strength of the toroidal magnets as well. So what's the strength of these toroidal magnets?
So the detector itself is something like 7,000 tons in weight. And what I know is that the magnetic, so force-wise, it's similar. There's many, I would say hundreds, if not 1,000 tons of force that they can exert. And we know this when we first actually turned on some magnets for tests. I think that the calorimetry, which is very, very heavy, was moved on the floor during the Big Bang. It didn't do any damage, but it was surprised everybody that actually it could move that. So at least hundreds of tons, if not thousands of tons of force they can exert. Now, the magnetic field varies. We built a very strange magnet. We built a toroidal magnet on the outside here. And as such, the field varies between, I think, half a Tesla and 4 Tesla or something like that. It can get very powerful in certain areas. Now, I'll tell you why. That makes life a little bit difficult for us that it's not uniform. But having a toroid was done intentionally. Obviously, it wasn't a mistake. You guys know in class that you make solenoids, by taking a wire and curling it around and then you plug it in and to a 12-volt battery or whatever you have handy, and you suddenly have a solenoid. And that gives you a nice uniform magnetic field. And in the center of our detector, we have a solenoid. And that gives you the tracks that curve like this or like that when you look at them in the XY plane. You see them curving. But we decided intentionally not to build a large solenoid to surround our muon system. The reason for that is because Mother Nature doesn't let you send your magnetic field down to infinity. It doesn't like that. You have to return your magnetic field. And so you have a return flux, which means you have to have a lot of material, a lot of steel or iron to bring it back. And that's why if you look at the CMS tracks, you see these beautiful lazy S, because the field went one way and then it came back the other way. So their muons have lazy S to them. We decided not to do that because when a muon has to go through a lot of dense material, it gets scattered. And so even if you measure it precisely on the outside with these precision detectors, you don't know exactly what happened in the center. And what we really care about is what happens in the center of the detector. You want to reconstruct back to the center. You want to know what happened at the collision point. And so if the muon got scattered, then you don't get as precise a measurement there. So instead of having a lot of material, we made a toroidal magnet system. So maybe I can show it from here. But each of the tubes that you have there makes a loop. And so the magnetic field goes in a loop. There's also toroids inside this. There's toroids inside there. There's also loops. So the magnetic field actually curves in a loop, which means Mother Nature's happy, no infinities. But it means that your tracking is really difficult to do because the magnetic field's not uniform. And you have to measure, you have to map the magnetic field at each point so you can tell what's happening to the track and you can reconstruct it, its momentum precisely. And also that whole system there structurally has to be sound. Otherwise it will try to collapse on itself. Unlike a solenoid, which just has pressure going inside or outside. So what I'll do now is I'll walk up some more and I'll take you up higher, but I can get some more questions.
And as Steve's starting to walk, I'm going to explain a bunch of links I've just added to the chat. And just like with Anya's session, I'll keep track of all these links. I'll put them probably in the next email I send to everyone with the invitation to Marco's session on Monday on Seeing the Invisible with Detectors. So if you miss anything and like you don't need to worry about frantically copying everything down, I'll save it somewhere. I'll make sure it's available. But to explain some of these links, the last one I put on, because that's related to the last thing Steve was talking about, he was explaining the toroidal magnetic field. And there are plans for making your own homemade version of it that you can make in the lab with students. Oh, cool. There's both a 3D printable model or one using drinking straws and cardboard. This was made a couple of years ago before straws were getting banned from sale in the EU. But hopefully most of you are like me and you have a lifetime supply of straws stockpiled in preparation for that. Just a warning, the one where you're making with straws and cardboard, it is really finicky. If you're doing it to set it up, make it so that you can test each, like there's 8 different loops of wires you're making the toroid. Don't just connect it all in series hoping you're not going to miss something out. Connect it so that you can test each part separately, because it's a nightmare to troubleshoot. But it is great that's available rather than the 3D printable one, because if you're like me, I was at a rich private school, but we still never managed to afford 3D printers. So it's great there's a cheaper alternative. And to explain
before you go on, I just wanted to show you while I stopped here for a second.
Yeah, please do, yeah.
I stop at different things that always fascinate me. This is simply mixtures, you know, because you need different gases in different areas. CO2, nitrogen, argon, and these are for the different detectors for them to work. Argon is inside the electromagnetic counter. This I always claim that this right here, this is our supply of dark matter, which unfortunately is still 0. But that's how much we've captured. Although we know it's everywhere, we just haven't gotten it yet. We're looking for it. Okay, I'll keep going up. I like to show these services. You see it by because this really represents the collaboration. You know, we have 6,000 people contributing to this, and every single thing here had to be installed. and bent, connected, tested, leak checked, and it always amazes me. It's really the idea that you could bring these people together from all over the world and have them build something which works as well as this is incredible. So, okay, I'll let you continue.
Well, and something incredible with that too is if you visit some of these people in other parts of the world and you see parts of the detector, like Jesus, who's going to be talking about the CMS gas chambers and their muon detection, he'll do it from his lab where he's got a couple of layers that are exactly like they made there. I think they were made there in Spain, and that's why they have those to test them and to use them for teaching purposes there. And last month I was in Bulgaria, and I was with Rumiana, who, Steve, you'd know Rumiana as well, I think.
Sure. Sure.
But she had these giant scintillators, which were the same ones that they sent off to CMS, but they kept a couple back in their lab for testing and developing purposes. And actually, the one that I saw, there was something wrong with it, and that's why it wasn't being used. But it was the biggest single scintillator I'd seen. It was like the size of a dinner table. And so it's amazing if you visit these people, you see the components that all come together from all these different parts of the world. But most of them, it's not just that like there's a factory and someone made them there, but it's the result of several years of research at usually a national level laboratory. And you can see teams of people who've worked on this rather than just everything together in the detector, where you might kind of skip over some of the parts because it's big enough. It would take a lifetime to know every detail of every subdetector. So it's really cool seeing the parts of the detectors in different parts of the world too.
Now I'm taking you up someplace you've never been. This is way up towards the top of the detector. Well, I came up here earlier in the year when we actually had the magnetic field still on it, and it was a little difficult because I have metal steel-toed shoes. It was possible. There's more services, lots of cabling. One of the most amazing parts is copper here. Like a giant pipe organ. And I'm going to take you up on top of the detector shortly. But if you have any more questions, feel free to ask.
Oh, there were a couple of questions that came through as well that were mixed between my links. So one was, do you have results every run, or sometimes you can't see any trace? And how much time does it take one run or one experiment?
Oh, okay. All right. So let me define some terms first, so it's kind of clear what I say. I'll turn this. I like it up here. I don't. I'm one of the very few people who gets to come up here, so I'm always proud to come up for now. So we're really up at the top, and I'm gonna take even higher in a little bit. So let me explain how things work. We unfortunately use the word experiment as a word to describe our collaboration and our device together. It's not really a good choice. Like we say, the Atlas experiment, CMS experiment, etc. In fact, true to the word, an experiment is happening every 25 nanoseconds. Right? Every time you have a collision, that's a new experiment. It's a new test. And then you get measurements from all these different experiments, and that's how we can confirm things. That's how we can say when we have a 5 sigma peak that we found something, because we've actually done enough experiments to show that we can reproduce it. And it's very clear that it's a signal over a background. So what we do, we break things up here into runs, but I don't think the word run that you're using is the same as mine, but a run actually lasts for about 3 or 4 years. Call that a run. We're now in run 3. We had the first run, which lasted a few years before we upgraded. We got to a little bit higher energy. We went from 7 TeV collisions to 8, so actually from 3.5 TeV beam to 4 TeV beam. In run 2, we did collisions at 6.5 TeV beam And then run 3, which is what we're at now, has lasted a little over a year. And we had a rough past year. For this past year, we mainly did heavy ion things. We didn't collide protons as much as we'd like to have because we had a vacuum leak in the accelerator. But we hope we'll catch up this next year. So a run for us is several years long. And many of our results are indeed sort of based on a run. You take as much data as you can during that run, and you combine it all, and you show final results. But in between, we have conferences, and we live from conference to conference. Conferences are very important things to us. So in between conferences, we're running our detectors and taking measurements, taking data all the time, nonstop. And then we're analyzing it at the same time. People are always analyzing data. So while the data is being taken, there's people on shift here, there's people fixing detectors or doing whatever they need to do or building the next generation of detectors. There's also people doing analysis. More than a third of the authors on our papers are PhD students. So they're doing analysis. Well, they're doing all the work. They're also taking shifts and doing all the work. But so the analysis is nonstop. And typically we prepare our results for the upcoming major conferences. And they usually happen either in the winter, we have some in February, March, Montreal, places, ski resorts, of course, or in the summer, major conferences called the International Conference for High Energy Physics, ICHEF, or LHCP, the LHC conference. And so then you have whatever preliminary results you have, you put together the data you have then, and you present. And this is a real competition time. We're working as hard as we can to get the best possible result because we're going to go see our peers from the other experiments. We want to have a better result than them. So it's a good competition. We sit down together, we show each other our results, we explain our methods, we learn from each other. And in the future, we do better. You know, we borrow each other's techniques and ideas. And sometimes we even can combine results from the different experiments. That's not always possible because they're very different, the detectors, and sometimes we do. So the results are nonstop. There's almost always some conference coming up. For the big ones, like ICHEP, the International Conference of High Energy Physics, we actually run the accelerator up until a few weeks beforehand. And we actually have to stop typically to prepare for that. And that's when the Higgs boson was presented in 2012. It was in preparation for an ICHEP, which was in Melbourne, Australia. And in fact, I had tickets ready to go. I knew they were going to show something, and then they decided, the CERN council decided it needed to be shown here. So, because it was a big result, it was a huge result for us. So that's how it works. We're continually taking data. Right now, we're done taking data, but people are doing analysis of that data, refining their analyses nonstop. I hope that helps.
And just related to the data, I've added 2 more links in the chat. It seems like I'm nonstop looking up links to put in there, but I've added a link to Atlas Open Data in case anyone's interested in accessing into the data themselves. Or a more simplified way of that is through the master classes. So I'll add a link to the master classes as well. And there were a couple more questions that came up. One, I guess it was at the last place you were asking if one of the things is copper wire, as in a solenoid. And I think a lot of the copper is tubing behind you, but I can't remember which thing you were looking at when that came up. So if Joanne could.
Yeah. So the copper that we use here is mainly a tubing for gases. All the magnets, pretty much all the magnets on the LHC, with the exception of Alice, are superconducting. So they're niobium titanium alloy, which was produced because if you cool it way, way down, and I mean way, way down, it's colder than the universe, so 1.9 degrees Kelvin, then it becomes superconducting, meaning there's absolutely no resistance. And that means that we can consume less power and get to higher magnetic field. And that's true for our solenoid in the center and true for the toroids. Now, what you see when you see the toroidal tubes is the tube is actually all of the cryogenics. You need to make a vacuum around where the magnet is. So it's all cryogenics. And you actually have heater coils on those tubes so that they don't cool down too much and get condensation on them. But it keeps a vacuum inside there. There absolutely has to be a vacuum, otherwise the temperature will be conducted. And then you got to keep it cold.
And then there was another question about calibration. So are detectors and other equipment calibrations done hourly, daily, continuously, or periodically?
Oh, great question. I mean, it depends on the detector, but what's typical is to do them perhaps daily. While when you're on shift, you're in the control room, which is way upstairs. If you watch the film Angels and Demons, it looks as if the control room is just across the way there, and there's a sliding glass door. That's not good. It's way upstairs. When we take a shift, during the day is often the time we do things, like if there's any repair that needs to be made or calibrations or alignments or things like that. But whenever the beam is down, then we do stuff. And often you do a calibration. Then in the evening, and especially the night shift, where you don't really want someone doing things, you want them just monitoring, then we're just taking data. Usually at night, all you're doing is taking data, monitoring your detector to make sure that everything needs to go. So typically during the day, but anytime it stops, anytime the beam stops and you're refilling it, because the beam lasts for a certain amount of time before the intensity is sort of gets to a point of diminishing return, then we dump the beam. It gets sent out into some blocks, and its energy is dissipated, and we refill with new beam at the higher intensity, and start collisions again. And during that time, it takes an hour or so to do that. The time that you can do calibration as well. The more calibration, the better, right? The more recent it is, the more precise.
And thinking of calibration, someone had told me, I forget if it was Alice or all the LHC experiments, but they were saying in times when there's not a beam line, sometimes they'll use cosmic rays to calibrate different parts of it because you'll be able to have, because there's available radiation even if you're not having collisions.
Right, you can do that. We use cosmic rays. We use a lot of tracks to be able to align our detectors as well. Can be cosmic rays. Usually that's when there are collisions, but yeah, you can certainly see cosmic rays. Cosmic rays pass through the detector all the time, like they pass through us, and sometimes they pass through the center. So if you looked at an image, you might say, "Oh, maybe that's from a collision," but it passed right through the vertex. But fortunately, we have timing detectors all around, and so you can tell from the timing of a track whether it came from the outside and left, or if it came from the center and went out in two different directions. So that's how we differentiate. You can subtract out the cosmic rays from a collision ray. I can take you for a walk through over the top. Not actually a whole lot to see here, but I find it really cool because more copper.
And while Steve's going over the top, does anyone else have any other questions? And again, feel free to use your voice and microphone if you're not shy.
I'll show you that the access shaft actually is way up there. Gives you an idea of how far up there. That's the ceiling of the building that's over the detector. And from here, it's probably about I don't know, 50, probably 50 meters or so up from here. And of course, we have to have some very strong training here to be able to install and take apart the detector. So one of the common questions that I've been asked is how, with a detector like this, how is it that we can be searching for dark matter? Because dark matter, what we know so far about dark matter is that it only interacts through gravity. We see it because of its effect on the stars in our galaxy. We can see that they spin at a rate that's just not right. If there wasn't something else inside there, that was Vera Rubin who made that discovery. And it's not just a small effect; it's 80 to 90% of the matter is dark matter. We've even been able to map it by lensing effects of distant stars and galaxies and clusters. And so they have some very accurate maps of dark matter, and it's still something like 85%. And yet we have a detector which can only really detect things which are electromagnetic in nature, or which have strong interactions. Weak interactions, not really. You have to have some huge neutrino detector to catch neutrinos. They slip right out of here without us seeing them. But with dark matter, it's going to slip right out. We're never going to see it. Our detectors, if we haven't seen it so far, they're never going to see it. But this is a really, really nice thing to show for students. A really good way to do conservation momentum. What we know, and I'll show you this. You guys probably all know this, but I really like this as a lesson. From here, so I'm way up at the top, and you can see our muon detectors here. These are the trigger chambers. We know that the beam comes in this way, goes all the way down, and in the middle of this detector, it collides with other photons. Well, what we know is that they're traveling exactly like this. All of the momentum is in this direction, this longitudinal direction. There's no lateral momentum to that. So when they collide, if you can add up all the tracks that come out and you project them onto this plane right here that's exactly perpendicular to the beam, then you know that you should be able to add them all up vectorally and get zero. There should be absolutely conservation of momentum. And that's pretty much the case. That's what we see most of the time. But as I said, sometimes neutrinos slip out. We produce them frequently. They slip out. But we have a model that's very, very precise, the standard model. And we know how they should, what the energy spectrum, the missing energy spectrum should look like. So we plot all of that energy that's missing. We call that the missing transverse energy, or the missing transverse momentum. We plot that, and we know what to expect from the standard model. So we look at that, and then we look for deviations at the large end for large amounts of missing energy or missing momentum that came out. And that will be the signal that tells us we have produced dark matter. And it's not completely, I'll show you our LGBT table. Beautiful job. It's not difficult to imagine that we could produce dark matter, because what we know is that we have found the Higgs boson. We know that the Higgs boson interacts with absolutely all elementary particles that have mass. And we've measured that, and we're still measuring that. We've seen it interacting with top quarks and bottom quarks, and W and Z boson, and taus, and charm quarks. And we're just now starting to see it interacting with muon. That's much more rare because they're much lighter. But by the end of next year, we will have a very clear signal of that interaction. So if we can produce dark matter, if it is an elementary particle uh, that obviously has mass because it interacts through gravity, then if we can get up to the high enough energy that we can produce it, we will see it. We will not see it. We can measure that we don't see it. How's that? I'm bringing you over to the other side.
Perfect. Does anyone have any other questions for Steve as he's walking over to the other side? And we'll wait. Sorry, what's that?
There's a little glimpse in between the detector part. The blue in there, that's the L8 too. Where the beam goes.
Oh, like that's a dipole, like the blue color there, and it shifts over when they open the detector.
Actually, it's shielding. So here the detector is in its normal position, unlike on the other side where we're doing work. So this is how it normally is when we're running. You have the MDTs, these are the monitored drift tubes. These are the precision position detectors. You can see that they go kind of in a circle, and that's because the muons, because it's a toroidal magnet, will curve this way and this way. All right, that's different than CMS, for example. Very different, and they get measured in these detectors here. And so the precision, that the measurement of the momentum, is done with these tubes. You don't care so much where they are along the tube as much as you care about measuring where they are relative to the wire. And in fact, the timing information you get from these chambers is so precise that we actually know at which radius away from the wire the muon pass. So you draw little circles, and the software gets little circles that it draws, and you make a track that goes through those circles, that goes tangent to those circles. One of the cool things you can see here is you can see the targets. So these things here are the targets that the cameras inside here focus on to know how much the detector has moved. Because you really, really want to know exactly the position of that to tens of microns. So the thickness of your hair is how well we want to know the positioning on all of this. So that's what goes on with that chamber. This is the trigger chamber here. These ground chambers, they give you some positions. They have strips in there which give you the position along the tube and in both ways. So they tell you something came through in a specific spot. The blue, again, it's shielding that surrounds the L8C. So inside there's magnets. You don't have dipoles here. Usually you have really no magnets in here because you don't want to curve anything. You have focusing magnets on the inside of the tunnel. And then here, the beams are just going straight and they curve right, they go right through each other inside there. So this is the normal alignment of the detector.
And there's a question about the diameter of the beam. Prior to the collisions, what is the diameter of the beam?
I don't know the precise number, but you can think of it something like a needle. It's a very, very fine diameter when they go through each other. And the finer, the better, right? So it's very. That's a good question, but I bet you can Google that before I could even calculate it. But I think it's something like a needle.
And
anyway, I've heard. Yeah.
I remember being told it's something like your pinky, so I'll look that up because I trust you a lot more than I trust my memory.
No, it could be. I wouldn't trust me. That could be too. I think it's hard to define because it's going to be more intense in the center. But it could be more like a pinky. That's true. I mean, I know that the analogy. Maybe I'm mixing up because the analogy for being able to make these collisions is that you take somebody in Paris, like Michael, and somebody in New York, and they each throw a needle at each other, and you have those two needles hit. somewhere over the Atlantic. I have no idea what that's referring to. But people were trying to somehow give some analogy of how difficult it is to make the collision. You can see here we have another access shaft up there. This is really beautiful. I'm going to stay around here. When I'm done, I'm going to be taking some pictures. This is really nice. You don't usually get to see all this laid out like this.
Okay, so I've looked up and found a bunch of different answers, but the one that seems most trustworthy at the moment says it's about 1 millimeter wide when they're far from a collision point.
Wow, that's even finer than a needle.
And then one thing that I think might have been when I was thinking like finger diameter, but that's not even the right dimension. I have here, it says 50 millimeters is the beam pipe diameter, which makes sense. The pipe would be a lot wider, but that's not even the size of that would be a very, very wide finger if it's that big a diameter.
Who has another question? Is the glider mounted on a shock absorber? That's a good question. It is a good idea to keep it from moving. We have actually a lot of sensors that give us information through vibrations at a certain time. And they're very sensitive. So we can look back in the data. And one of the things I remember after it happened, there was this terrible earthquake in Indonesia. It happened early on when the LHC was just built. And we were able to look back in the data and see that. So that's really opposite here. But there was enough shocks that went through Earth that we could measure that. And I mean, it is true, we are close to the Alps. And so there can be vibrations sometimes. You think maybe there'd be earthquakes. Very, very few. I've lived here for, 2 millennia so far. And in that time, I think there was one small tremor near Annecy that some people said they felt. I didn't. There isn't much seismic activity. And it used to be that our Alps were growing, but I just heard recently that they're shrinking now. And that's a sad story because it's because of the melting of the glaciers. So the ice inside them is melting, and as such, the mountain is shrinking. Maybe there's another question? Got to be more questions.
I'm sure someone's got to be curious. Well, while waiting for another question, I guess I never got around to explaining the links I added for other virtual visits. So I wrote a note to visit CERN online ones. They might not be currently available. So part of the story behind that is they developed a lot of virtual visits during the pandemic. The past year, a lot of people working on that have been very busy with the opening of Science Gateway. And most of their virtual visit offer, like for general CERN facilities or for things that aren't an LHC experiment that run their own, like Atlas, then they've been phased out. So they're not advertised as publicly available. Probably if you ask the right people, they'll still do it for you. Like I'm sure they still remember how and they have the right equipment. But there's not a link where I can say, here's a link, ask for that. But that gives me an idea, and teachers, like you don't need to feedback now, but over the course of the next several weeks and whatnot, let me know if you'd be interested in other visits, because if you don't know how to ask for them, I can ask people who have run them before, things like that. And if there's interest, like even for a group of teachers like this, I could request ones for the new year as well. So that's something that could come up. But the CMS one, CMS being the other very big detector on the LHC, they still run their own virtual visits. So there's a link to that in the chat. And then there's some online resources that CERN visits put together during the pandemic before they started testing the virtual visits. That website's still on there. So if you want to have like, you can navigate with things like Google Street View through a bunch of facilities. Almost all of that stuff's still online. Like you can wander around the data center, you can wander around a lot of the experiments. So a lot of that stuff is still there. You just can't necessarily request a visit like of the antimatter factory or of the magnet facility, things like that. So it's kind of a long explanation, but that explains like the couple of sentences. Maybe you can't request it now. That's kind of the story behind that.
Yeah, okay. I mean, for Atlas, we take all the requests. Usually we can handle them all. And there's many other people besides myself. Mohammed Al-Hoop runs them, and he's recruited quite a few people. We have young people who do it, young physicists, young women as well, which I think helps provide a role model for your students. I think that's rather important. So if you just let us know, we can get something going on here. Here we have a very simple form you fill out, and we try to take care of it. We have virtual visits during the year as well when we're taking data. We just can't come underground here like this. So we do it from above ground with our control center in the background. You can see the control room behind us, which has got a lot of activity in it.
And if anyone's interested in seeing what it looks like Steve showing around the Atlas control room, I'll find a link somewhere of the last visit where, for my virtual science camps, it was a group of kids, and some teachers. He showed us around the control room. And they had recently done it up. It was about 2 years ago they redid it, but the control room is really well done for visits too. So that's definitely worth considering even when the beam line's on. It's a great thing to show students. And I don't know if you mentioned, Steve, often people can request in the language of their country. It'll depend if there's a guide who comfortably speaks that language. But for a lot of reasonably well-spoken languages, there's probably someone on Atlas guiding, right?
Yeah, we do have quite a few people from different places. We're happy to try to do that. Also, it pushes us to try to get more people trained. We have, the typical languages. We have English, Italian, French, German. But even
and Spanish, like there's a lot of Spanish speakers signed up, so that'll come up as useful too.
Yeah, we do the best we can try to find someone who can do that.
And I would imagine, although like I'm not on it, so I don't know for sure, but I would imagine if someone requests a language that no current guide speaks, Mohammed might try and think, oh, is there anyone on Atlas who speaks that? Can I use that as an excuse to recruit a new guide? I mean, maybe he doesn't try that, but like knowing Mohammed, that seems like the kind of thing he might do. So it's worth asking for any language and just see what comes up as the answer.
Okay, who wants to know more about particle physics, life, the universe, anything? Any questions are good. What's happening next? I had a group this morning, actually. I got to come down here with a small group from Microsoft, and they were in the petabytes, terabytes, and how much data is going and how it flows through the system. We produce a lot. If we took all the data, all the time, all the collisions, it'd be hundreds of terabytes per second that would be coming out of it. And we have to reduce that way down. And we keep the stuff that's interesting and clear off the rest. We still end up with tens of petabytes per second. I mean, represented per year, tens of petabytes. There was a question about radiation.
Yeah, what's the level of radiation outside the detector when the beam is on?
When it's on?
Yeah.
So when it's on, no one's in here. There's radiation here. Although, actually, if you're far away from the beam line and from the collision point, it's not so bad. But I wouldn't want to be in here. You could I think I calculated that once you could actually come in here during beam for about an hour and you get your annual dose. If that's what you wanted. But we have a lot of radiation monitors. Most of the radiation happens in the center of the collision. And out here you get high energy gamma rays, you get high energy neutrons, but there's this is the wall. Nothing's going to go through that. There's concrete all completely surrounding it. So if you can't come into this cabin. There's an interlock which prevents you from being able to come into the cabin. If you try to open the door, it will turn off the LHC. So there's nothing in the nearby area. There's zero, exactly zero. And when we come here, when there's no beam, we take a dosimeter with us. I always have to wear my dosimeter. We take one with us for the visit, and it's always at 0 microsieverts, which is really nothing. It's less than a banana of radiation. It's nothing down there. But the actual level really depends on how close you are to the beam.
And there's other facilities at CERN where there's more of a concern for radiation as well. Like offhand, they seem to be more concerned at Isolde where they're making different isotopes. But maybe you can think of other places where like you'd expect higher radiation than LHC detectors.
Well, probably a testing facility where we're intentionally irradiating. There's maybe more risk there. But these detectors, we've been very, very careful. Nothing gets outside. Caverns have been accelerated. I think I saw some question about undergraduates.
Yes, undergraduate internships. And Steve's in charge of the undergraduate program for the University of Michigan, I think. So he probably knows a lot about these programs.
Yeah. There, in the summertime, we have an REU program. So the National Science Foundation supports research experience for undergraduates. And we have one that's cited here. That means we select students from all over the U.S. and they come here and then they become part of the bigger program. So CERN in general has a summer student program. Some 250 to 300 students, undergraduate students, come here over the summer for roughly 2 months each. And so they're part of that. I get 15 students from the U.S. They come here and they're part of this big 250 program. That's the thing that I run in the summer. I also have a group of Michigan students, specifically the person I used to work for was a big advocate of undergraduate education and research. He helped to really found the REU program in general, which is all over the U.S. now. When he died, he gave money to the university to support a certain number of students. So we get several students who come here on that grant. And then also the local U.S. mission to the international organizations gives me some funding, which I've been using to fund women and minorities from the U.S. But this year we're funding 3 Ukrainian students who will be coming over here in January. They'll be doing research on different experiments here. I'm looking forward to that. We had 3 Ukrainian students last year as well who came here with the U.S. students. And it's nice to give them an opportunity to do something away from the war that's devastating their country, and also to help to prepare that country to rebuild itself in the future. So that's a really wonderful thing. They enjoyed it tremendously, and they're now in universities in the UK and in the US studying. So yeah, there are programs. Mainly the programs are the summer. I've really tried advocating for many years to have a larger program during the fall and winter semesters. We did try that out. It worked very, very well. We had some funding from another foundation. The Richard Lounsbury Foundation funded that. And it was really a big success story. But unfortunately, we couldn't find someone who would give funding for the long term. They only gave short-term grants. And so I am still bugging people in the US. In fact, in a week, I'm going to be flying back to the US. And one of my intents is to bug people about funding more programs during the semester. And I think that other countries could do that as well. They could send students here for a semester to do research. There's a big difference between the summer and the semester. The semester, they can focus on a project. In 3 months, you can get a tremendous amount of work done and write up a thesis, which can be a part of their undergraduate education. I highly advocate that. If undergraduate students are interested, the best way for them to do it is to find a university that is doing research here, and to just talk to the professors and say, hey, I would like to work on that experiment. And they'll probably find someone willing to help to do that.
Those are really great programs. That was a good question to ask. Does anyone have any last questions for Steve?
You don't want to know what's next? I'll tell you anyway.
I'm curious what's next. Steve, what's next?
What's next? So we're going to run for a couple more years in the configuration we have now, where we have slightly higher, it's run 3, higher luminosity than the past. And then we're going to shut down for a couple years and completely rebuild the inside of it. The tracking system will all be completely rebuilt. And that will happen also for the other experiment. As the LHC is upgraded to an even higher luminosity, what we call high luminosity LHC. Luminosity is very important. That's the number of collisions you get per second. And that means that we can look for rare processes, very rare things that have a low probability of being produced. The probability is everything for us. That's how you can tell with it, right? We don't know collision to collision exactly what happened. All we can do is look at the products and see how many times you see certain types of events happening, and then calculate probabilities from that. And that's where our theory comes from. It's something that you use to calculate the probability of different interactions happening. So the more collisions per second, the better precision we can make, and the better chance we have of finding something that's different than the standard model, because we still don't have explanations for dark matter. We aren't even near an explanation for dark energy, which is why the universe is expanding faster and faster. We don't know where gravity comes into the equation. There's many, many huge questions that we have out there. You know, gravity is what, a millionth of 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 the strength of electromagnetism. So we just don't yet see how we're going to measure that. But it's big question we have. So the next steps after we've done this will be the high luminosity LHC for several years, 3, 4, maybe 5 years. Have another long shutdown, again, improve things, maybe higher energy, higher luminosity. Finally, while that's going on, we're already studying new technologies, potential of making a linear collider to make collisions of electrons at very high energies, so we can produce lots and lots of Higgs bosons and measure them more precisely. So the quick linear collider, or the ILC, which different countries are interested in potentially hosting. China is interested in building a collider, perhaps to produce Higgs bosons, perhaps to explore with protons afterwards. And we're looking at building an enormous ring, potentially 91 kilometers around, not this dinky 27-kilometer thing, to go to even higher energies and to explore a whole new realm, which could help us answer a lot of these questions. So there's a lot of things being worked on. And the one last thing I'll tell you that's really super cool is the idea of making a muon collider. You're producing muons, which then decay instantly. They don't last very long, but they go to higher mass and then higher energy. And so that's something that we're really looking into. So I see everybody's got to take off. I do as well. Thank you so much for joining us.
Locked in for the night, right? No, you don't.
Yeah, I hope I'm not locked in here.
Oh, but someone in charge of security gets mad when you're there at this.
If I stay too late, they'll get upset. So, and it's a Friday evening, so I should get going. But thank you so much for bringing everybody to here. It's a pleasure to host you, and I hope you'll come here in person sometime. And I hope you'll get your classrooms to connect with me. It'll be a lot of fun.
And so on that note, hopefully everyone will get their classrooms to visit Atlas with Steve or one of the other great guides. Thank you again, Steve. It's always a pleasure, and I always learn new things. Every time I talk to you, not only when you show the Atlas detector, but every time I talk to you. So it's always great seeing you again. And for the teachers, look out for the link for Marco's session, Making the Invisible Visible with Detectors, where he'll go through some of the science of detectors, but with a hands-on activity using bubble chamber tracks. So all the stuff Steve was saying about momentum, charged particles curving in magnetic fields, you'll go over activities you can actually use in classrooms to teach that on Monday, in Monday's session at 7:30 Central European time, or like Paris, Geneva time. So thanks again, everyone, and thank you again, Steve.
Okay, thanks, Michael. Take care, everybody. Have a great weekend. I hope it's not